Today we start with state observer designing part 3. In this we will study introduction to minimum order observer and design of minimum order state observer matrix. Now about the introduction to minimum order observer. As we have seen that the state needs to be measured, but sometimes it is not possible to measure the states. So, in that case instead of going for unmeasured state, we are estimating all the states of the system. That means, even though there are some states which can be measured and which cannot be measured. So, what we are doing, we are estimating all the states, that is called full order observer, whereas some of the states which can't be measured, that only estimating, and remaining states which we have measured we keep as it is. Then that type of technique is called minimum order observer, or we can say that type of design is called minimum order observer. That means, we have to estimate the states which are not possible to measure only. That means, suppose the system has n state and there are say m states which are say measured, and this is n, that is called total states. So, n is called a total states and m which can be measured states. That means, we have to only estimate n minus m states. So, when we are estimating only n minus m states, that is called minimum order observer. Now, we will see how to design this minimum order state observer matrix. As here there are some states which are to keep at is, that is the states which we have already measured, that actually we have to do measurement, and the states which can't be measured, that only to be estimated. That means, in a total states there must be some segregations, division. So, that means, if you see the mathematical part of it, it is somewhat complicated in comparison to the full order observer. Although if we derive it, we find it simple, but the process is somewhat laborious. So, now we start with the designing of minimum order observer. So, we as per our original convention, we have plant x dot equal to ax plus bu and y equal to cx. Now, in this case x is the state. So, this x involve both the thing, one is measured as well as unmeasured. Therefore, we write this x involvement of known state, this x involved known state and also unknown state. So, this can be represented as x a n and x b u n, that is unknown. So, this is known and unknown. That means, the state matrix has been divided into two parts, known and unknown. So, now this can be represented for simplicity, say x a and say x b. Now, we have to do the analysis of the system. So, let us say there are say 10 states. We can say that the 2 states are known and 8 are say unknown. But now, for simplicity purpose, what we are doing, we are assuming that we knows only one state, that is one state is known and other state need to be estimated. Therefore, we can write like this x a n equal to x a is a scalar quantity equal to y that is directly measured, and this x bun equal to xp that is unmeasurable portion of state vector. So, it is measured, it is unmeasured, whereas we are taking a measured state, only one state, that is scalar. So, x a equal to y, which that is directly measured. Now, we write this matrix as x a dot x p dot that is equal to, now this matrix that is x dot equal to x. So, in x dot we have x a dot x p dot, where x a dot is measured, x p dot is unmeasured. So, now this has to written in terms of matrix form, that is A matrix can be written as A suffix AB, A suffix BA, A suffix BB, and now here state as XA XB plus this is BA and BB into U, and output Y can be written as 1 0 and here XA and here is XP. So, in this particular system we have what we have done, we know y equals to 1, that is XA output, and here U matrix related to U matrix where B has BA part and BB part, and and here this is XA XB and this is A matrix. Now, in this equation this AA is a scalar quantity and here A suffix AB, this one. Now, this is a quantity of 1. So, it can be represented as 1 multiplied by n minus matrix, that is 1 row n minus 1 column. Then ABA is written as n minus 1 into 1 matrix. Then here ABB is written as n minus 1 multiplied by n minus 1 matrix. And about this portion, so this portion BA is a scalar. It is because we are assuming that XA involved one value, one quantity, one only measured, remaining are unmeasured. Therefore, BA we written as scalar, and here B suffix B is written as n minus 1 multiplied by 1 matrix. So, here dimension of all the elements in the given matrix A, B, C we have written. That means, here this is A, this corresponds to B and this corresponds to C. So, all the information we have written. Now, from this part XA dot equal to A suffix AA XA, AB XB plus BA into U. So, that we can write down as XA dot equal to AA XA plus AB XB plus BA into U. So, now these equations we have written. So, after looking after these equations, so we observe that here this XA dot minus this AAA into XA minus BA into U into AAB into XB. So, what we have seen that in this particular equation this XA dot is there, AA into XA and BA into U, these are the known quantity. That means, in a given state space equations we have taken one particular state which we known, and from that state we have observed that these particular portions is the measured portion and this can be written as ym equal to AB into xb. That means this shows the relationship between the measured part and unmeasured part. So, this particular part we can use as a output equations. Now, from this equation xb dot equal to ABA into XA, ABB into XB plus BB, the B suffix B into U, that indicate the unmeasured portion of the state equation. Therefore, we can write this as, that is, unmeasured portion can be written as xb dot equal to ABA into XA plus ABB into XB plus BB into U. Now, here also we will find that this ABA XA plus BB into U, ABB into XB. Now, this portion ABA XA BB into U, that is the known quantity in the unmeasured state equations. That means this particular portion or this particular part is called unmeasured. This portion is called unmeasurable portion of the state equation, and this particular part is the known part. This is the known quantity. So, now here we have written the equation for measurable state as well as the unmeasurable state. Now, we have to compare the full order observer state equations as well as the reduced order observer, or we can say the minimum order observer state equations. So, here we know that the full order observer equations can be written as Ax dot equal to Ax plus b. So, here we know that this x, that is the state which we can directly estimate it. So, all things are we know. Now, the state equation for the minimum order observer that is xb dot equal to ABB into XB plus ABA into XA plus BB into U, and here is the known quantity. Now, the output equation for full order observer we can write down as y equal to Cx, but here the output equation for minimum order observer, it can be written as Ym equal to AB into XB. In last part we have derived the output equation of the full order observer. So, the output equation for the full order observer can be written as, that is, output equation for the full order observer can be written as Xc dot equal to A minus Ke into C into Xc plus Bu into Ke into Y. So, similarly here also we have to write the output equation for the reduced order observer, or we can say the minimum order observer. Now, in order to get this, we have to compare the elements of the full order observer as well as the minimum order observer. Now, let us take the elements of A matrix. So, now for that purpose, first of all we write a table full order observer, and here minimum order observer. Now, in a full order observer, we have A matrix, that is, we have x dot equal to ax plus bu. So, it is a matrix. Now, coming to the full order observer, in a full order observer, in case of minimum order observer, we have xb dot, that is corresponding to the xb dot. This is the ABB, this is the state, and this is the in terms of input, because we are knowing. So, here for minimum order observer, we write A suffix BB. Now, coming to the B into U matrix, that is x dot equal to ax plus bu, this is BU. So, BU in a full order observer, it corresponds to here ABA into XA plus B suffix B into U. So, now we have written for the state equations. Now, about the output. Now, in case of output, in case of full order observer, we are written as y, and where in minimum order observer, we are written as ym, and this ym equal to xa dot minus aa xa minus ba into u. So, we can write down this as ym. Now, in full order observer, we have a K matrix, and the order of this K matrix is n cross 1, and here in case of minimum order observer, we can write down as this KER n minus 1 cross 1 matrix, this KE and here KER. And now, about the C matrix. The C matrix in case of full order observer, we can write down as C. Now, here we will find that this ym output equal to AB into XB, that is nothing but the C. Therefore, we can write down as this as A into AB. So, all these elements we have written. Now, from this we write the output equation for minimum order observer as here, instead of here XBE dot, that is equal to ABB minus KE into R into AB into XBE plus this B into U. So, B into U here ABA XA plus BB into U plus here instead of KE, here we can write KER into Y, this is as YM. That means, this can be written as ABB minus KER AB into XBE, here ABA into XA, here BB into U, and this here KER, this YM is XA dot minus AAA XA minus BA into U. So, now these equations we have solved. Now, we have to see the point. Now, here we have got the state equation for the minimum order observer xb dot, but now here xa dot is there, that is y equals to xa, and in the state equation we get xa dot, that means noise is there, it will amplify and that create problems. Therefore, we had to remove the effect of xa dot, that means in our equation there should not be terms like xa dot. So, in order to handle this, so what we can do here, we write the above equation as xp dot minus this part k into xa dot, we can move the left side. So, we write KER to xa dot, now here ABB minus KER into AB into XBE, and here ABA, now XA is common. So, here KER into AAA into XA plus BB minus KER BA into U. So, what we have done in these equations, that is from this to this KER into XA dot we have moved on the left side. So, XB dot minus KER into XA dot in bracket this ABB KER into AB into XB, that remains same. What we have done here, this XA is here, any XA that we have to take common. So, we have taken XA common and the elements we have written as ABA minus KER into AA plus BB, B suffix B minus KER, this KER into B into U. Now, again this equation need to be simplified. So, here we can write down as ABB minus KER into AB. So, now what we write, we have the equations, state equation in terms of KBE dot minus KER into XA dot. Therefore, in the output we have to represent the equation in terms of XB minus KER into XA. So, what we have done, ABB minus KER into AB multiplied by XBE minus KER into Y plus ABB minus KER into A into AB multiplied by KER plus Y. That means here ABB minus KER into AB into XB. So, this equation is this part, and now this KER minus AB we have to make written additional term minus KER into Y, and now this term need to be nullified. Therefore, here what we written ABB minus KER into AB plus KER into Y plus, now this to be written here ABA minus KER into AAA into Y, this X is Y plus BB KER into BA into U. Now, this equation need to be simplified. So, in order to simplification what we write, ABB minus KER into AAB. Now, here XBE minus KER into Y plus, now here what we will do, we have to take this Y common, and therefore, what we can write this as ABB minus KER into AAB to KER plus ABA minus KER into AA plus Y plus, and now this portion will write like this, BB minus KER into BA into U. That means, after getting this, we are coming with this particular step. Now, we again simplify it. So, in order to simplification, what we write, this XB minus KERY we write in terms of new variable, that is XB minus K into Y, we can write it as XB minus K into XA. Let us say it is as T, but now in our equation we have KBE minus KER into Y equal to XBE minus KER into XA equal to TE, and therefore, here XB dot minus KER Y dot equal to T dot, and therefore, this equation XB dot minus KER into XA dot, that is T dot equal to ABB minus KER AEB into T plus ABB minus KER AB to KER plus ABA minus KER into A suffix A into Y plus BB minus KER into BA into U. So, now what do we do? Now again we simplify it. So, just looking after this one, we find that this working of the minimum order observer is somewhat complicated or mathematically laborious, but still as we have to do the analysis, we have to proceed further. So, therefore, this portion we can write down as AE equal to ABB minus KER into AB, and now here BE can be written as this portion. This part is AE into KER plus ABA minus KER into A suffix A, and here FE can be written as this portion BB minus KER into BA, and therefore the final equation is T dot equal to AE into TE plus B into Y and FE into U. This is the equation for a minimum order observer. And now about the output equation. For output equation, this Y equal to 1 0, this XA and XB, and now here this XC can be written as, now here XA is known and XB is unknown, and we have to write this equation in terms of this state, that is in terms of this TE. Therefore, this equation can be written as 0 I n minus 1, here XBE minus KER Y plus 1 by KER into Y, and here this portion that is this part is represented by as CE, and this part is represented by DE, and therefore we have this XC can be written as CE into TE and here DE into Y. So, this gives a transformation from TE to XC. So, now all the mathematical part we have derived. So, we will find that in this case there is a design of minimum order observer, then there is a transformation, and then the state will transfer to U. Therefore, based on this we will now draw the block diagram of minimum order observer. So, in this case there is a original plant, this test space plant. Now, here is C, here is output Y. Now, here is matrix B, and here is A matrix. Now, we have state x dot, and here is x, and now here is control input U. Now, this is the original plant. Now, we have to draw the block diagram of a minimum order observer. So, in this case we have state which is coming, that is here T dot, and here it is coming with integrator. Now, here is TE. Now here the matrix AE and from this U we have a matrix FE is coming here, and here is a matrix BE and it is coming to output Y, and afterward there is a transformation that is in terms of CE, and here is DE, and from this we will get XC, and this is nothing but your KC, and it goes to input U. So now this particular portion we call as a transformation, and this particular part, this part is called minimum order observer. That means here we will find that this is the original plant, this is the minimum order observer, and finally we have to transfer to the controller the complete state where is the involvement of the measured state as well as the unmeasured, and therefore this transformation is needed, and finally the complete state is be transferred through XC, which is involvement of our measured and non measured, and this is the actual control KC, and it will move here. Now about the observer equations, observer error equation. Now here observer error equation is XB dot equal to ABB minus KER into AB into XBE plus ABA into XA, here BB into U plus KER into AB into XB. So earlier we have seen these equations. Now the original state equation for XB dot is given as ABA into XB plus ABB into XB plus BB into U. So this is the unmeasured portion and this is the measured estimated portion. So here we write this as XP dot minus XP dot. So if we subtract this from this, what we will get? You will get the equation as ABB minus KER into AB into XB minus XBE, and now this XB as XBE we can write down as error equations, and it is in terms of T minus TE. Therefore this E dot equal to ABB minus KER into AB into E. So this particular called the error equation for the minimum order observer, and from this we can get the observability condition as that is AAB into ABB, and this process repeated will get AB into ABB into n minus 2, and it must have rank of n minus 1. If the rank is n minus 1, then observability condition is satisfied, and from this we can design a controller, this KER as phi ABB into, this is observatory conditions QB. So, this write QB inverse, and here we write and 0 0 1, and here phi ABB is equal to ABB n minus 1 alpha 1 E ABB n minus 2 plus alpha n minus 2 E into ABB plus alpha n minus 1 into I. So, this KER gives you the reduced order controller. So, we have seen that the process for estimating the minimum order observer. So, full order observer as well as reduced order observer, or we can say minimum order observer, both can be applicable, but as far as the analysis part is concerned, we will find that the analysis of this minimum order observer, it is quite laborious, and main purpose is to main purpose of all these things is to design the controller. But now here the controller which we design based on the desired pole placement as well as the observer we are design, that is also the based on the some trial and error procedures. But we need some techniques where we can get the optimal controller design. So, that is the part of the LQR. So, now till date whatever we have studied that is concerned with the pole placement which is based on the trial error procedure. In future we can also try for the design of controller by means of optimal pole placement. Now, these are some references: Ogata, D. Rai Chaudhary, Stephanie. Thank you.